Okay, so we've made it to section 1.3. We're going to start out by talking about linear functions. We have the general form of a linear function, or in other words, slope point. And basically you can derive this expression here, or this template you could call it, for the general form of a line by simply using the slope and a little bit of algebra. And then we have the standard form, or what's usually called the slope-intercept form. So in example 1, we want to write the general and standard forms of the linear function for which f of 1 equals 3 and f of 4 equals negative 3. Okay, you have to realize that these equations can be translated into ordered pairs. Okay, had a little bit of trouble with my pen. But as I was saying, f of 1 equals 3 can be converted into 1 comma 3. And then f of 4 can be converted into f of 4 equal negative 3 can be converted into 4 comma negative 3. Alright, so if we take this equation, the general form, f of x equals y1 plus a times x minus x1. Okay, we see that we need 1 point, y1 and x1, for this general form, and then we also need the slope. Okay, the slope is calculated as y2 minus y1, so we can't just get by with only having 1 point. We need 2 points to calculate the slope. So the top is just the difference in the y coordinates. The bottom is the difference in the x coordinates of the 2 points. And remember, with subtraction, the order matters. So you can start out with y2 as either 3 or negative 3. So for instance, if I choose to use 3 as my y2, second point, and then subtract. Okay, this subtraction symbol comes from subtracting or taking the difference of the y's. Now I'm going to have to take this negative 3 and insert it along with the subtraction symbol, so I get a minus minus. And then on the bottom, since I chose the 3 from this point that I labeled second, then for the x's I want to use 1 first, and then subtract the 4 from it on the bottom. So 3 minus 3 becomes 3 plus 3, and then 1 minus 4 becomes a negative 3. So we get 6 over negative 3, which ends up being negative 2. Okay, so I'm going to write that up here. A equals negative 2. I'm going to make myself some space. And now I'm simply going to take this equation, the y and the x with the subscripts. I want to substitute those with the x and y coordinates of one of my points, and it doesn't matter which one. So since I labeled this one first, and I've got a subscript of 1 here, I'll go with these coordinates. And so for y1, I substitute in negative 3. It's plus a, and so I have plus a negative 2. I'm just going to write it as minus 2. I keep this x. It's just sort of my input variable. And then I subtract x1, and x1 is 4 since I went with negative 3 for y1. So insert a 4 here. And this is my general form of my linear function that passes through these 2 points. Okay, I could clean this up a little bit if I wanted to. -3, distribute the 2, and I would have a -2x plus 8. Combine the -3 and the 8, and I have a -2x plus 5. Okay, and it turns out that this is going to be my slope-intercept form. Okay, if you compare it to this formula, then we have ax plus b, where a is my slope that I calculated, -2, and b is plus 5. And so that means that this line will cross the y-axis at y equal 5. Okay, so we're going to go about this a different way. Starting with the slope-intercept form, f of x equals ax plus b. Alright, I've already calculated my slope. It'll be the same no matter what form we use because our 2 points are the same. I'll go ahead and substitute it in for a. It sets in front of the x variable, and so I'm left with b, which I don't know because these 2 ordered pairs are not my y-intercept, and I know that because the x variable is not 0. Okay, f of x, I am going to use y in its place, and so what I need to do now is substitute in one of the pairs of my coordinates. I'll go with the first, or I'm sorry, I'll go with the second ordered pair, and so I have y equal 3, and then I have x equal 1, and we plug those into this formula in the place of x and y so that now I can calculate b. So we have a 3 on the left, minus 2, and to solve for b, if I simply add 2 to both sides, I see that b equals 5 again, as I found before, by simply rearranging the general form of the same line passing through the same 2 points. So now that I've found my b, I can go back to this equation, keep my y and my x, and plug in b, which is 5. Same equation that I had before. So now we're going to get started running through some base function, which we'll use in the next section when we talk about horizontal vertical transformations. Our first one is it's also a linear function, but this one is specifically called the identity function, because whatever we put in for x, if we make a table of values, whatever number I put in for x is just simply the same as my output. Okay, f of x equals x is the same as y equals x. So if I say x equals -5, then y equals -5. If I say x equals 0, then y equals 0. If and I can pick decimal numbers. If I say x is 2.1, then y is 2.1. Okay. So is it even or odd? Okay. One way to tell is to look at the exponents of the variables. If they're all odd, then it is a odd function, and we only have one variable here and the exponent's 1, so it's odd. Or I can simply take the graph of my function, okay, cut the graph of my function along the y-axis, rotate 180 degrees, compare that to the right side, and you should see that they're identical. So the identity function is symmetric with respect to the origin, meaning it is odd. Okay, what's the domain? Well, if I plug in any number, I just simply get that number back. We see this function and we don't see radicals, we don't see a x variable in the denominator, so there's no restrictions on the domain, and therefore we write negative infinity, positive infinity, interval notation, all real numbers. I can put in any number that I want to in this function and I will get a number back. Well, what about the range? Okay, well, it is also all real numbers. Okay, so if I put 1,000,000 in, I'll get 1,000,000 back. Okay, if I put in a very small number, negative 300 billion, then I'll get negative 300 billion back. So domain and the range are real numbers. Okay. Another way you could look at it is if you look at the graph, this simply points down, okay, and to the left, and so it is going to span across the entire y-axis. Okay, this function continues to decrease forever. So there is no y value that it will not pass on its way down, and same argument for the top. Okay, as we go from left to right along this line, it's a straight line. It'll continue to go straight and up, and so eventually we will reach any number on the y-axis that we choose. It spans the entire y-axis, so the range is all real numbers. Okay, what about the x and y intercept? Well, this line passes through the origin, and for a function we only want one output per input. So if I input the y-axis coordinates x equal 0, then I'm only going to get 1 point along the y-axis. So there's only, if it's a function, we only ever get one y-intercept. So passes through the origin, so that would be our y-intercept. Okay, and it would also be our x-intercept. Okay, a lot of times we might say x-intercept x equals 0, or y-intercept y equals 0, or you could say b equals 0. What about a local minimum or a local maximum? Well, this line, this function has a constant slope. It continues in a straight line. It never, okay, as we go from right to left, okay, it never changes its slope. It never turns back up. Okay, so we never create a local minimum. Does not exist. Likewise for local maximum, it does not exist. It continues to increase forever. It never decreases again once we start to walk from left to right along this function. Okay, it never changes its slope, so we'll never have a local maximum. Increasing on, in this particular case, we have a linear function that has a positive slope. So from left to right, it always points in the upward direction. Therefore, it always increases. Okay, and we're referencing this interval to the x-axis. It increases on the x-axis from negative infinity to positive infinity. Okay, now this particular function never decreases since it always increases. So we would say for this interval does not exist. If we had a different linear function that had a negative slope, then this relationship would swap. It would decrease over all real numbers, and the increasing interval would not exist for a negative sloped line. But here, for these characteristics that we just listed, we're specifically referring to the identity function. Our next function that we're going to talk about is the squaring function, or another name for it would be the parabola. This is our basic squaring function, x squared. You probably remember seeing other functions. I'll give it a different name. This is also a parabola, and they're similar in the sense that we have the x squared component, except g of x has a constant added to it off to the side. Okay, so is it even or odd? Well, if we were to fold along the y-axis, then the two halves would overlap. So it is an even function. Or in other words, if we look at the algebraic expression for the function, we only have even exponents, 2. 2 is even. So this is an even function, symmetric with respect to the y-axis. What is the domain? Well, a parabola sort of looks like it's curving upward, and then eventually it slows down with respect to the x-axis. It almost looks like it begins to go straight up. But it does span out across the entire x-axis, from to the right, negative infinity, and over to the left, negative infinity. Okay, positive infinity to the right. Okay, so domain is all real numbers. Okay, we're simply taking a number and squaring the input, and I can square any number. Okay, I can take really large positive numbers, 1,000, square it, and I'll always get a number from squaring another real number. This would turn out to be 1,000,000. Okay, I can square the negative of 1,000, and I still get a number back. Okay, 1,000,000. So no matter how big or small, I can square the number and expect to get a real number back. However, for the range, there are certain values on the y-axis that we can never get by simply squaring a number. Okay, as I just stated, squaring the number, if we square a positive, we get a positive number back. If I square 0, I just get 0. Now, if I square a negative number, I begin to get more positive outputs. Okay, so whether it's positive or a negative number. If I square it, I get a positive output. So in other words, our y, our range, only includes real numbers from 0 to positive infinity. Okay, and in the sense of a local minimum, okay, we have a local minimum there at the origin. From negative infinity along the x-axis, we drop down, touch the origin, touch the x-axis. Once we pass the origin, the squaring function starts back up and it never returns. It never comes back in this direction. So we don't go any lower than the x-axis. Okay, x-intercept, y-intercept. Well, squaring function simply touches the origin. So once again, for both the x and y-intercept, we have the origin. Local minimum would be the origin. If you are standing at the origin and you look to the left and you look to the right, then the curve is higher than the spot you're standing. It increases on both sides. So local minimum 0, 0. And as I stated before, once we leave the origin, it increases on both sides and it never returns. So this is our only local minimum. Local maximum, there isn't one. We only have a minimum. Once this function starts making its way up towards y equal infinity, it will never drop back down. It will never curve back downward. Likewise, on either side, it does not do that. It continues up forever. It increases. Okay, so no maximum. Increasing intervals, and with increasing and decreasing, we want to make sure that we orient ourselves in the sense that we go from left to right on the x-axis, from negative to positive. Okay, so going from left to right, if we start over here on the left, then y is decreasing until we get to our local minimum. Once we're passed through our local minimum, y begins to increase. Okay, so that splits our squaring function up into two intervals, one increasing, one decreasing. So the first one, from left to right, we would say starts at negative infinity and continues until we get to the origin, to our minimum. Once we pass through our minimum, we increase. Okay, so the increasing interval starts at 0 and continues to infinity. Cubing function. Okay, we only have this term in the function, and the x variable has an odd exponent. So we only have an odd exponent. The function is odd. Or, once again, I could take our graph I could cut it along the y-axis, rotate that half 180 degrees and compare the two sides, and they're identical. So we are dealing with an odd function, symmetric about the origin. What is the domain? Well, as stated before, I can put in as large a number as I want to, and I'm simply cubing it, so my output is going to be larger if I input a number greater than 1. Okay, I can put in numbers less than 1, cube it, and I will always get a number back. I can put in very small numbers, okay, smaller inputs to the left. I can put in as small a number as I want to, cube it, and I will definitely get a number back. So cubing a number isn't necessarily restrictive in the sense of domain. So our domain turns out to be all real numbers. What about the range? What kind of numbers can I expect to get from my outputs? Okay, well, let me put some of this information back in. If you look at the graph, this half on the left continues downward indefinitely, and the right side continues up indefinitely, and in between we pass through the origin. So we will span the entire y-axis, so we would get all real numbers. Another way to look at it is to say, if I cube a positive, I will get a positive number. If I cube a negative number, I will get a negative number. So we can get outputs from both halves of the y-axis. X and y intercept. Well, this gets a little redundant. With the cubing function, we pass through the origin again. So both the x and the y intercept would be the origin for this specific case, x to the third. Local minimum, well, there isn't one. Okay, it may look like up through here around the origin that it flattens out, maybe even goes back down, but if you look very closely, you should see that this curve, as it passes through the origin, always increases. If you put in a larger x value, you will always get back a larger f of x value. So we don't have a minimum or local minimum, and we do not have a local maximum. Okay, the cubing function does not go up and come back down. Okay, it simply goes up, slows down, but still increases, and then continues upward. Increasing, well, as I just stated, and in this case we want to erase that arrow, because again, for increasing and decreasing intervals, we want to consider the left to right direction only, in the sense that we travel from left to right on the x-axis. Okay, and we talk about, well, what is the y coordinate doing, or the output doing, as we go from left to right? Okay, from left to right, this piece is obviously increasing with respect to y, and then if we track our way along here and we get to the other half, it's also increasing. So all real numbers for the increasing interval. And again, this function never decreases, it never cuts back down. It only increases with each step to the right along the x-axis. Okay, what about our square root function? Well, here is a graph of it. It simply begins here at the origin, and it increases fairly rapidly in the beginning, and then it sort of looks like it starts to flatten out, but it doesn't actually flatten out. It increases indefinitely. So, is it even or odd? Well, it is neither. There is no symmetry with respect to the y or the origin. We only have a piece of the curve on one half of the graph. So it's neither. What is the domain? Well, this is one of those special cases that we talked about concerning domain earlier. The two cases that we look for are a radical and when we have x in the denominator of a function. So in this case, we do not want x to be negative. We want it to be greater than or equal to 0. So our domain is from 0 to infinity. And if you look at the graph, you can see that it simply begins at the origin and it travels to the right, covering all of the positive x values. And then the range is also from 0 to infinity. Once it begins at the origin, it travels upward. Okay? And as long as you put in a larger value of x, you will always get a larger value for y. So it may look like it'll never reach infinity, but if you put a big enough number in there, you can get as large a number you want for the range. So the range is 0 to infinity. X and y intercept the origin. Okay. If I take our function and put in 0 for x, square root of 0 equals 0. So we definitely pass through the origin. Well, maybe not through, but we reached the origin. X and y intercept the origin. Local minimum. I am going to say that our local minimum, our lowest point, is the origin. You could also call this the absolute minimum. Local maximum, well, once we leave the origin, the function always increases. So we never start to decrease. We can never go up and then break back downward. It always goes up. So we'll never create a local maximum. Does not exist. Okay, increasing. Well, we are going to put parentheses beginning at 0 and continuing out to infinity. From left to right, our squaring function increases. If I put in a bigger x, it will result in a bigger f of x. Decreasing interval does not exist. Okay, cube root. We don't run into the same trouble that we do with the square root. Okay, cube root has an odd root number, and so it is possible to put in negative values for x, and you can easily see that in the graph of the cube root function. Before, we didn't have this piece on the negative half of the graph. Okay, so for instance, if I use a negative 8 as my input, the cube root of negative 8, what do I raise to the third power to get a negative 8? Is a negative 2. Okay, so we can have negative numbers for our input, and we can get negative numbers for our output, in that we are below the x-axis for our output. Okay, is it even or odd? Well, I suppose you may be able to consider the exponents, but in this case I think it's clear if we just simply observe the symmetry. So if I cut the left half with respect to the y-axis, and I simply take that half and rotate it 180 degrees and compare the two halves. They're identical. So we are dealing with an odd function. Okay, so I can put in positive and negative numbers. So our domain is the entire real number line. Any x, any number can be inserted for an x value. Range, you can see that with respect to the y-axis, from the origin we increase, and then from the origin going downward it decreases indefinitely. If I go far enough out on my x-axis to the left, if I put in a large enough negative number, I can get as large negative y value as I want to. Okay, so the cubing function spans the entire y-axis, so all real numbers for the range. And again, cubing function passes through the origin, and so it's our x and y intercept. If I insert f of 0 or 0 into f and take the cube root, what do I raise to the third power to get 0? Well, that's just simply 0. 0x, 0y gives us our origin coordinates. Local minimum does not exist. Local maximum does not exist. Okay. Increasing on the entire number line, and it never decreases. Okay. If I continue to put in larger values of x, then f of x will always be larger. Absolute value function. It's pretty distinguishable. If you're looking at a graph, it simply looks like a V. It could be upside or downside, like that. But we're not talking about the upside down version. We are talking about a positive absolute value of x. So I'll erase that. Is it even or odd? Well, it's symmetric about the y-axis, so it is even. Okay, what about the domain? Well, absolute value function is just simply going to take a positive number and map it to its identical positive version. So for instance, absolute value of 2 just simply gives me the 2 back. On the other hand, if I take a negative 2 or any other negative number, it will give me the opposite in return, positive 2. If I put in a negative 5 into my absolute value function, it will return a positive 5. And then if I put in absolute value of 0, how far is 0 from itself? I get 0. Okay. So I'm not restricted in the sense of what numbers I can put into my absolute value function, but we definitely have a restriction on the range. Okay, so like I said, no matter what I put into my absolute value function, I'm either going to get a positive number back or 0. I cannot Out of just this basic absolute value function, I cannot get negative numbers for a range, and so I would use the interval from 0 to infinity for my range. And you can verify that by looking at the graph. If you go out from the origin to the right, or you go out from the origin to the left, y simply increases. We do not go down below the x-axis. We only span the positive half of the y-axis. Okay, so the range is 0 to infinity, positive numbers. You could also write this as x is greater than or equal to 0. Okay, but for whatever reason, I usually prefer the interval notation. X-intercept, you may be tired of seeing this, is the origin. Okay, absolute value function passes through the origin. As I show here, if I insert a 0 for x, my output y would also be 0. So it does pass through the origin, and that serves as the x and y intercept. Local minimum, well, we hit a bottom at the origin. If you're standing on the origin and you look left and you look right, then both sides of the curve would, or the immediate sides of the curve would increase. So local minimum at 0, 0, and as far as the local max, there isn't one. Once you leave the origin traveling to the right, it increases forever, and once you leave the origin and travel to the left, it increases forever. It never reaches a peak to where it travels back down on either side. This does not happen. It continues up indefinitely. Increasing. So we definitely have some increasing and decreasing behavior. Again, traveling from left to right along the x-axis, what is my y coordinate doing? Well, on this half, if I were standing on this curve and I was going to the right, I would be going downhill. So the left half is decreasing and the right half is increasing. Increasing is from 0 to infinity, and I've seen books express this with either a bracket or a parentheses. I think WebAssign uses parentheses in any case, whether your limits are infinity or a number. Decreasing from negative infinity to 0. Okay. And so we're just representing this left half increasing the right half. And finally, our reciprocal function, 1 over x. Okay, and reciprocal should be a familiar term. We used it in intro. If I take the reciprocal of a fraction, then I simply swap the denominator and the numerator. So the reciprocal of 2/3 is 3 over 2. Okay, and a reciprocal function is a rational function. So in this case, you shouldn't be surprised that we have a vertical asymptote at x equal 0, because we cannot enter in 0 for x. If we did, we would get 1 over 0, which is undefined. Okay, any other number, we can place it under 1 and we'll be okay. The only restriction is that x cannot equal 0 in this case. And as far as asymptotes go, the degree of the numerator is less than the degree of the denominator. The degree is 1 on the bottom and 0 on the top. So we have a horizontal asymptote at y equal 0. Okay, it turns out this function is odd. If you simply take the graph and you chop off the left half and rotate it, as we've done several times already, and then we rotate and compare the two halves. They are identical. So we are definitely dealing with an odd function. And now the domain. Okay, as we said before, the only restriction is that x cannot be 0. So we're going to have to break our domain up into two intervals, one for x less than 0 and one for x greater than 0, and we will plant a union symbol in between those two. Range, same case, doesn't have anything to do with x equals 0. It has to do with the horizontal asymptote, such that y will never be 0. Okay. X and y intercept. The y-axis is the horizontal asymptote, and the x-axis, oh, I've got those backwards. The y-axis is the vertical asymptote. Let me just erase this y here. The x-axis and the y-axis is the vertical asymptote. Now, the vertical asymptotes never crossed. Okay, so there is no y-intercept. With a rational function, you can actually cross the x-axis, but not in this case. That doesn't happen. So we do not have an x-intercept either. Now, local minimum or maximum, these do not exist. Okay, increasing, if we orient ourselves going from left to right, on the first half we are decreasing. Okay, and we'll simply put a parentheses with 0. We can't include 0 in the domain, or 0's not in the domain anyway. And then if we pick it up on the right side, again we are decreasing. So we would simply write, maybe I could scooch this over. I don't want to do that. I'll just erase it. And I want to write them side by side. Okay, it never increases, so this interval does not exist. Okay, so that sort of concludes our list of basic functions that we're going to write out the characteristics for. Just keep in mind that if we change any of these base functions by inserting numbers or adding numbers, then it can change these characteristics. But at least for the base functions, you have a starting point. You have some information to think about. Okay, piecewise functions. We've simply just have a function, and in this case, it's separated into two expressions. We have x squared minus 1 for f. On the other hand, we have a 2x plus 1. Now, keep in mind, we said piecewise functions, so we do not want two outputs. And we will not get two outputs for 1x if we follow the instructions that are given off to the side. So here we have some inequalities. This simply says that if we insert an x, if we have an input x and it is less than or equal to negative 1, then you want to use this expression x squared minus 1 to calculate the output. If you have a number that's greater than negative 1, then we use this bottom expression, 2x plus 1. So graphically what we can do is find our reference number and simply draw sort of a boundary between the two halves. And then I will create two tables. Okay, this first table will apply to x values that are less than or equal to negative 1. This second one, x greater than negative 1. Okay, in reference to my graph, I can say left and I can say right side. Okay, and so the left is going to be the portion that is less than negative 1. The x's are less. So the expression that we're dealing with is x squared minus 1, and on the right we have 2x plus 1. Okay, so for the left portion, I will start with a negative 1 and calculate the output. Negative 1 squared minus 1 gives me a 0. Okay, and since this part is a parabolic shaped function, I'll do probably 3 points. Okay, 3 inputs. Okay, now for x, we want to start choosing values less than negative 1. So I will go to the left on the x-axis and choose negative 2, square it, subtract 1, and I'll get my output. So here I have a 4, subtract 1, I get 3 for output. And here if I insert a negative 3 and square it and subtract 1, I will get 8, but notice that 8 is not labeled on my y-axis. It sort of jumped off my graph, so I can fix that by simply going over here and calculating a more appropriate output for an input that's actually on my graph. So let's plot these 2 points first. I've got a negative 1 and a 0. And notice that I put a solid dot because if you look at the inequality, we do have an equal to bar there. So I can insert into the x squared minus 1 exactly negative 1. Okay, I'll plot my second point, negative 2, 3. So here is negative 2. And I go all the way to the top of my y-axis to plot this point. And past that, I'm gonna, if I choose a number smaller than negative 2, I'm gonna shoot off of my graph. So what I'll do is I'll be smart and I'll calculate the output for negative 1.5. It falls in between negative 1 and negative 2. Negative 1.5 squared is 2.25, and if I subtract 1, I get 1.25. Okay, and I'm going to have to kind of estimate this. I am going to eyeball it, and I'm going to place my point right there. just above positive 1 on my y-axis. Okay, if I wanted to, I could just go ahead and sketch my curve, and it should be parabolic. Once I hit this last point, my y coordinate will increase pretty rapidly. Alright, so I want to kind of draw a little bit of a curve in it. It is parabolic. Now, I'll work on the right side. I will also use -1. Okay, I want to figure out where this half would start on this x equals -1 line if -1 could be used for this expression. Okay, so 2 minus 1 plus 1, I get a -2 plus 1, -1. Now, since -1 isn't included in this inequality, then what I'll do at the location of these coordinates is I will put an open dot there. Okay, and I'm going to use it for one of my points to plot this line. Now, for this half, I have a linear expression, so I really only need to plot 2 pairs of coordinates for the right half. So now I want to pick a number bigger than -1, and 1 is one such number. 2 times 1 plus 1 will give me, let's see, we get 2 plus 1, 3, almost went off my graph. Okay, so I'll go over here at x equal 1. I'll erase these labels up here. One and y equals 3, and now I just simply try to draw the straightest line that I can through these points. And I could put arrows on both sides to show that they continue to increase beyond the edge of the graph. At this point, I am done. So I will move it on to the next piecewise function, g, and follow the same procedure. I'll create my 2 tables. I will take note of sort of my reference point, 0, and x equals 0 is the y-axis. Okay, so x less than 0, that is this left side, and x greater than 0 is the right side. Okay, so over here I want to use 2x minus 1, and on the right minus 3x plus 5. Okay, I'll pick some numbers that are less than 0, but I also want to do 0 for both of them, just to see where they start on my y-axis. The negative 3x plus 5 will have the solid dot, at x equals 0, and the 2x minus 1 will have the open dot at x equals 0. Why? Because if you look at the inequality symbols, this one does not have an equal to, and this one does have an equal to. Equal to, solid dot, no equal to, open dot. So let's calculate some coordinates. 2 times 0, 0 my input, subtract 1, negative 1. 0 is always a nice number to use. Now I want to pick numbers less than 0, negative 1. 2 times negative 1, minus 1, and I get negative 3. I'll go over here and go ahead and plot my points. Remember, I have an open dot at x equals 0 for this left piece. And then at -1, I want to go down to -3. So I'll track my way down here. -1 is well within the domain for this portion of the function. So here I'm just really plotting regular points. I have nice linear expressions for both halves. So I'll just simply draw a straight line. I only need 2 pairs of coordinates. What about the right half? I have a -3. I use 0 as my input plus 5. 5 is my output. And then I put in a 1. -3 times 1 plus 5 gives me a 5 minus 3. 2. Okay. Now this 5 shot way off my graph, so I'm going to plot an extra point. I'm going to use x equal 2, -3 times 2 plus 5 equals -1. And that is within the space of my graph. So 1 corresponds to y equal 2, x equal 2, and y equal -1. So I drop down 1 below x equal 2. And now I will try to draw a straight line through these as best I can. At some point, this line will touch the y-axis and stop. And if I were to continue this upward, once I touch the y-axis, I would put a solid dot. Okay. And on the right end, I can put an arrow to show that it continues downward and to the right. Both segments are linear. Okay, the greatest integer function, kind of a neat function. In that you can probably see down here the graph of it looks like a staircase. Okay, so why is that? Also note the symbol for the greatest integer function is basically sort of a double bracket, okay, which is not the same is our absolute value bars. These are two different functions. Okay, this one just sort of looks like absolute value. Okay, so this is probably most easily explained by drawing a number line. Mine is not very flat, but we'll put some numbers on it. To the right, I want to be positive. To the left, I will be negative. Okay, and so it says we want the greatest integer that is less than the number inside, or if it's an integer inside already as our input, then we just keep that particular integer. So if we look at this one first, f of -1, well, -1 is an integer, so I will keep that one. Okay. Now the other ones, you have to realize that the inputs on these others are not integers. We've got a 0.4. 2.4 is not an integer. 2.82 is not an integer. We have the 0.82 on the end. And then 3.7, we got 0.7. 1/2 is 0.5. So again, this is a decimal number with digits to the right of the decimal point. So we can't just simply use these numbers that we were given. Let us look at -2.4. Well, if we plotted it on our number line, it would fall somewhere in between -2 and -3. If we look immediately to the left, the first integer that we run into is a -3, so the output for f of -2.4 is -3. If we look at 2.8, it would be located over here, pretty close to the 3, but we go to the left because it says it wants the greatest integer less or left of that particular number, and that integer would be 2 for 2.82. Okay, so with the greatest integer function, we always look to the left on the number line. Where is -1/2? Well, it's 0.5 to the left of 0. If we look to the left, the first integer that we run into is -1. F 3.7. I'll extend my number line to include 4. And here is about where x equals 3.7 would land. If we look to the left, first integer that we see is a 3. Okay, so here we have a graph of it. Like I said, it's kind of neat. Looks like a staircase. If you say, okay, let's sort of try to make a little bit of sense of this. Say we go over here and to one of our input values, x equals -1/2. So f of x is this. Okay. If instead we, let me see, insert our -1/2, and we've already worked with this input, we get a -1. So if you look here at x equal 1/2, we drop down here to y equal -1. Okay, so let's go over here and just pick a number that we didn't have as an input. Let's say 1x equal 1.5. Well, luckily we already have a number line, okay, the x-axis. So 1.5 itself is an integer. We don't keep 1.5. We look immediately to the left, and the first integer that we run into is 1, and that is our y-coordinate. So for x equals 1.5, we go up to y equals 1. And so for any of these numbers in between 1 and 2, we are simply going to plot our y as 1. Because if we're in between 1 and 2 and we look to the left, we will always see 1 as the first integer. So we just get a flat line through here. Let's look at x equal 3. Well, 3 itself is an integer, so 3 is going to map to y equal 3. So we actually have the input here. So if we wanted to perhaps make our graph a little more accurate, we should probably go through here and put in open dots, because 3 wants to skip past this y2. That may or may not be obvious with just the horizontal lines themselves. We can put an open dot here and then a solid dot on the end of the y equals 3 bar. Okay, so in the beginning of all of these, we could just simply put open dots on the right and solid dots on the left. And that sort of makes it more obvious that we don't have multiple inputs for one, or multiple outputs for one input. Okay. And we've sort of reached the last example. And now we don't just simply have the greatest integer function, we have that plus it too. So to calculate f of -1, we will put it inside the greatest integer notation and put a +2 off to the side. -1 itself is an integer. -1 plus 2 would give us 1. So f of -1 is a 1. Greatest integer less than -1/2 is a -1. We add 2 to it and we get a 1 again. The greatest integer less than 2.82 plus 2 would be 2 plus 2, 4. And then finally, the greatest integer less than 3.7 would be a 3. And then we just add a 2 to it, and we get 5. And that concludes section 1.3.